P8.19 shows an amplifier using utilizing a current mirror Q2, Q3. Hence, Q1 is a common source amplifier fed with V input is equal to VGS plus VT. Okay, where VGS is the gate source DC bias voltage of Q1 and Vi is the small signal to be amplified. Okay. Okay, let's go continue. So small signal to be amplified, find the signal component of the output voltage V0 and hence all small signal voltage gain V0 over Vi. Okay, this one is small Vi. This will be capital I. Okay, V0 over Vi. Also find the small signal resistance of the diode-connected Q2 in terms of GM2 and hence the total resistance between drain of Q1 and ground. What is the voltage gain of the CS amplifier Q1? Neglect all ROs. Okay. So first what we are going to do is we are going to draw the equivalent model circuit because that makes the problem simpler. So if you look at the equivalent model for an NMOS amplifier, if you remember, the equivalent model will look like this. We will have the gate drain on top, gate drain on top, and then we will have the gate drain and the source on the bottom. Okay, and the current ID current is also equivalent to GM-VGS. If you want to know how is that, like I derived in my previous video, like you can watch my previous videos. I derived in a video that for small signal equivalent model, in that one I derived the ID to be this. So this exact current is the ID. So here we can, instead of the current, we can express this like a GM VGS. Okay, and this is our gate, this is our drain, and this is our source. And if you look at this diagram, the source is connected to the ground, so we attach a ground to this, and there will be a resistance, output resistance between drain and the source. The drain is right here, source is right here, and the output resistance will be right here. Okay, this is an equivalent model. This is for the NMOS transistor, but for the PMOS, this is just flipped. If you flip this one, then source on top, ground on the bottom, like that. It just complete flip, and the current will be flowing bottom to top. So that's the difference. Other than that, and also the voltage right here is VGS because ground source. The voltage between ground and source is VGS. Okay. Other than that, that is basically it. So using that, we can draw the complete small signal model for this given circuit. Here we have a NMOS. You can see the arrow pointing outward. And here we had two PMOS on top. You see the arrow pointing inward of the gate. So the bottom one is NMOS and the top two are PMOS. So the circuit, equivalent circuit model will look like this. So gate for the bottom one, which follows exact same pattern like this. Gate, and then we have the drain, and then we have the source on the bottom. The source is connected to the ground. And here we will have the VGS voltage. In this case, that's going to be V capital I. Okay, it's small Vi. So this is going to be the gate source voltage because the source is connected to the ground, so there's no voltage. VGS is nothing but VG minus Vs. So VG minus 0, that is VG. So VG is whatever the voltage we have right here, that is in this case Vi. So we can say VGS is equal to Vi as well. Okay, and what else? And the current flow through this, that is GM VGS, And since we have 3 of them, so we can name it as GM1, VGS1, something like that. Or you can say GMVI as well, because VGS is equal to VI for the first one. So the current must be the VGS must be VI. So this is, let's name the first one as GM for the transconductance, and VI is for the VGS. Okay, and here we will have the load resistance RL. Okay, and if we look at the top MOSFETs are connected with this, and if you draw the equivalent model, it is like flipped. This is an NMOS, this is a PMOS. PMOS is like flip of the NMOS. So this is going to be like, look like this. The current is going to be in the opposite direction. It's going to go upward right now. Okay, and this one is let's call this one GM2, VGS2. VGS2, and the current is going upward, and this one is for the NMOS, plus minus, plus on top, minus on the bottom. For the PMOS, plus on the bottom and the minus on the top. Okay, and we have another PMOS also parallel to it, so we can draw that one right here, and that one also, the current goes upward like this. Let's call the current through that as let's call this one GM2, VGS2. This is GM3, VGS3. Okay, and this one also plus on the bottom, minus on the top, and this will be just grounded on the top right here. Okay, this is the equivalent model of the complete circuit. Now we can find whatever we want to find, and also we have a V output between the RL and the VO, that is over here, V output. Okay, so let's look at the question. The question is asking us to find out the V output, so let's try to find that one first. To find out the first one, V output, what we can do is we can look at the currents here. Let me go to a new page and create the equation. If you apply KCL on this node, whatever the current entering must be the current exiting, or addition of all the current is equal to 0. In this case, both of them are exiting, so we can say addition of all the current is equal to 0. Therefore, the GMVI GMVI plus GM2 VGS2 should be equal to 0. Okay, just apply the KCL at that node. Therefore, if we rearrange this one in terms of GM2 VGS2, this should be equivalent to negative GMVI. Therefore, VGS2 is nothing but negative, let's call this one GM1. Okay, the first one, let's keep it as GM1. So this is GM1 VI, GM2. So this one is going to become GM1 over GM2 multiplied by VI. Okay, let's call this one equation number 1. We can use that later. And the output voltage here, if you apply Ohm's law, this current times the resistance right here, V is equal to I times R. The current through this is GM3 VGS3 and the resistance here is RL. So the output voltage right here should be VO is equal to, we can say the output voltage is VO is equal to, and you see the current is like, we assume this direction to be positive, so this direction is negative, so this is going to be just negative GM3 VGS3 times the RL. Okay, that is our output voltage. And here if you look at VGS2 and VGS3, this one is VGS2, this voltage, and this one is VGS3 voltage. These two are in parallel, so this VGS3, these two are in parallel, so the voltages are equal. So instead of VGS3 you can also write VGS2 as well. VO is equal to negative GM3. Instead of VGS3 we write VGS2 times RL. And so this is, let's call this one equation number 2. This is the expression, we already have the expression for the V output. Okay, this is one of the answer. And the reason I changed this one like this, because there's another question asking, find out the voltage gain V output over V input. So if we keep VGS2, that's helpful because we have an equation of VGS2 related to VI, the V input. So what we can do is, instead of VGS2 we can plug this one in and find the ratio of VO over VI. Let's do that. So this is going to be, this is GM3 VGS2 times RL. Okay, let's rearrange this one. VGS2 is right here, so let me just straight away apply this. Now we are trying to find out the input output ratio. So we know that VO is equal to negative GM3, and instead of VGS2 I apply this one, so that's gonna be negative GM1 over GM2 times VI, and negative cancel, so this one become positive. So now this is going to be GM1 times GM1 times GM3 divided by GM2 times VI. Let's bring it to new page. So the VO is GM1 times GM3 divided by GM2 times VI, and we are interested in VO over VI. That is basically, and also I forgot RL as well. There should be an RL also multiplying everything. Yeah, there should be an RL multiplying everything. So this one also multiplied by an RL. And if I bring the VO over VI to the other side, then we still have the GM1, GM3 over GM, the bottom one is GM2 times the RL, and that is our gain. Okay, and here we can also furthermore simplify by looking at the circuit. If you look at the circuit diagram, the top two are PMOS. For the PMOS, if we write the transconductance expression, we can cancel a lot of things, because if you look at the transconductance equation, that is given by GM. For example, let's say I'm writing the transconductance expression for the 2. So GM2 is basically mu PCOX times width over length times V over drive, and the length is equal for everything. Okay, width might be the one changing, and in the question they haven't mentioned, I think. Let me see. So they didn't say it is matched or anything, so width, we assume the width is different, but length is always the same. So what happens here is GM3 also going to have a similar expression, that is mu p cox, mu p because this is PMOS, and that's why the GM1 doesn't work because that's an NMOS. So that for that one, this is mu n cox, and W2 over L. So we are looking at GM3 and GM2. W3 over L, and then V over V. And if you see, if I put this one on top and this one on the bottom, then this terms cancels, the L term cancel, V over V cancels. So that one becomes, in this case, W3, GM3 is on the top, so W3 over W2. So this one is going to be GM1 W3 over W2 times CRL. This is another way you can express the V output over V input. Okay, so that's basically it. And let's look at the next one. So the next one is asking for also find the small signal resistor diode connected transistor Q2 in terms of GM2, and hence the total resistance between drain of Q1 and ground. What is the voltage gain? So we have to find out the resistance, the total resistance between Q1. Find the small resistance of the diode connected transistor Q2 right here. Okay, so to do this one, what we can do is we can get rid of all the independent sources. We can set the independent sources to 0. For example, this Vi, if I set the Vi to be 0, then this one becomes an open circuit, and we will have a equivalent model that will look like this. Okay, we have ground on top, and then okay, we are just looking at the VS2 and VS1. This current source is GM2 VGS2, and now if we remove all the independent current sources, then we are gonna have something like this. We can say the new voltage as Vx, and the current flow through this we can call it as Ix, and the voltage right here is minus plus. The voltage right here is VGS2, and we are interested in finding this R in resistance, and this one will be connected to the ground. So this is the equivalent model after we remove all the independent sources. So it's going to look like this. Once we have that, we can find out the R in expression in terms of GM2. That's the question is asking for. So to do that, we have to look at the current. Current is nothing but this current is equal to this current, because the current cannot go anywhere else because we don't have any other branch. So this Ix is equal to GM2 VGS2. Let's express that one right here. Ix is equal to GM2 VGS2, and this VGS2 is nothing but this exact same voltage. So instead of VGS2, we can replace it with Vx as well. So Ix is equal to GM2. Instead of VGS2, I put the Vx, and therefore Vx over Ix is equal to 1 over GM2. And if you look at the Ohm's law, Vx over Ix is the resistance, that is this Rin. So Rin is basically 1 over GM2. So when we do that, we just have to make all the independent sources to be 0. We did it for the V input. The V input we set it to 0, so that one become an open circuit, and the equivalent model became like this. Okay, the last thing we had to do is we had to find out the gain. They're asking us to find out what is the voltage gain of the CS amplifier Q1. Okay, so to find out the gain is nothing but negative GM times the resistance. So total resistance between drain and the ground, total resistance between drain and the ground. In this case, we already know the total resistance with drain and the ground is Rin, so we can put that one in here. So this is negative GM times Rin, and we also have the expression for the Rin, that is 1 over GM2. This is GM1, 1 over GM2. So A is going to be equal to negative GM1 times 1 over GM2, which is nothing but A is equal to negative GM1 over GM2, and that is our gain. And that is it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys.